Hello, I'm Bradley Chippi. I'm going to be talking about building a simple blockchain in Python. This is for the Michigan Python group meetup. Want to give me a follow? There's my GitHub at the bottom. All right, so getting started. So we are going to build a simple proof of work system that mimics the simple functionality of a blockchain. And we'll be using SHA-256 as their hashing algorithm of choice, the same hashing algorithm Bitcoin uses. So a lot of words here, proof of work system, SHA-256. We're going to go step by step and go through what all these means and get the foundational learnings that we need before we start building our simple blockchain in Python. So what is proof of work? Proof of work is a cryptographic proof in which one party proves to others that a certain amount of computational effort was performed. To verify that work, it must require a minimal amount of computational power. So Bitcoin uses proof of work as the foundation for a consensus view of its decentralized network. And I have a source. I don't know if I don't have the chat still. Let's see if I can. So let's see if it's easy. Copy. I'll just post it in the chat for everyone. All right, cool. All right, so a little bit of history about proof of work and everything. So there was, this came out in like 1997, 1999. It was called Hashcash. Really weird name, in my opinion. It's, the hashing part makes sense, but the cache part doesn't for what it was. But basically, Hashcash was one of the first systems to utilize proof of work. And Hashcash's purpose was to prevent and limit email spam and denial of service attacks. So basically how that worked, and I'll give more examples in the next upcoming slides, but think about it as like your computer has to do some kind of computational effort. And basically, if you try to just spam a service or whatever, think about it, you're kind of going to do a denial of service on yourself because you have to do some kind of computational effort. So basically what that does is kind of not really bottleneck your CPU because it's most likely running on one thread or whatever, however it's programmed, it depends on every scenario, but basically it's just, you might think of like CAPTCHAs is how we use it in today's world. It might ask you to, what are these numbers and letters in this picture or whatever, the old school CAPTCHA. But then you also have like those CAPTCHAs where it's like, here's a picture of a train, pick all the pictures with the train or whatever. So this one's pretty neat because it's just like your computer does the CAPTCHA or your computer does that work for you. And I'm going to show an example. But Bitcoin's white paper by Satoshi Nakamoto, which is that anonymous, creator of Bitcoin, references the Hashcash paper. And I'll go ahead and I'll post this in the chat as well. All right, so here's an example. Let's see, I hope this GIF works. Okay, cool, it's working. So this is like proof of work CAPTCHA that someone built, and the source is right here. But as you can see, he's going to go ahead and create a comment, and you can see that POW CAPTCHA is going to work, and it's doing 36 hashes per second. But basically, it's a pretty neat idea of having your computer has to do that work before you can do that. So it prevents that denial of service. Potential denial of service or sending out too many requests. So people can't just go spamming comments or creating accounts or sending emails or whatever. So pretty neat concept, idea that they had back in the day for Hashcash. All right. So we'll keep moving on. So a SHA-256 hash, what is it? So that 256 means 256 bits, and you've probably heard of SHA-1 or MD5 or other hashing algorithms, but with SHA-256, it's 256 bits, divide that by 8, that's 32 bytes. And then basically, the output of that hashing algorithm is, and if we, with a hexadecimal digit, as we can see, I put the table here just so people can kind of visualize that, but there's 4 bits for every hexadecimal. So, as you can see here, 1010 is a capital A. So anyways, 256 divided by 4, it's a 64 hexadecimal digit string is basically the output of SHA-256. And I'll show examples of what a SHA-256 hash looks like. But anyways, a hash function is used to map data of any size to a fixed size. So no matter what I put in, so as I get like a UTF-8 encoded string and it's, I don't know, says I love Python or has a whole, I don't know, 100-page book or whatever, no matter what, it's going to be that fixed size of 64 hexadecimal digits. And no matter how long the input is, the output of the hash should always be the same. So if I put in dog, the hash is going to be, you know, whatever it is, ABC 1, 2, 3, you know, 64 size, but, and then you put in dog again, it's the same exact hash. So the output should always be the same if the input is always the same. The output should always, or should not be reversible, meaning you cannot calculate or guess the input by looking at the output. So looking at that long string, you know, that 64 hexadecimal digits, you shouldn't be able to guess what that input is, or even calculate it, reverse it in any which way. Small changes to the input should be significant changes to the output as well. And I'll go ahead and put this in here. Yeah, and I'll get to questions. I saw that, Dan. So I know there could some questions here. I'll ask for questions right after this one. So right here, so I have a UTF-8 encoded string that I'm passing into my SHA-256 function. Here's an example of what that output would look like. Here's another example. I love Python, completely different, very different. As you can see, the blockchain is so cool. There's that example. And then I'll just run through this demo right here. So basically, this is just a really cool site to visualize hashing, blocks, blockchain, all kinds of stuff. I really like it. It's been out for a while. But anyways, if I type in anything here, like I was saying, dog is CD635. Type in dog again, CD635, as you can see, like I was saying. I type in 1, 2, 3, 4. You can see that the hash is always changing a lot. And that's just the you know, the way the SHA-256 hash is. And like I was saying, if we take this, you know, the length is, that's 64 hexadecimal digits right there, characters. So that's SHA-256 in a nutshell. So does anyone have any questions so far?
No questions in the chat yet.
Yeah, you feel free to put a question in the chat anytime, and then I'll answer it. I'm paying attention to it. So, all right. So what about a collision? So you do hear about these collisions that happen. You probably heard with SHA-1 and stuff like that. Everyone's migrating off of SHA-1. It's actually been pretty outdated for a while, but you know, there is always, with every hashing, you know, algorithm function, you know, there is the potential of a collision. So long story short, the probability is not 0, but it is close to 0. And I got this number off. I found it last night because I was actually wondering it before I, you know, was going to present this. And I found the source, Avera. Does anyone remember Avera? Maybe if I show the logo. I haven't touched this, but this is like an old school, like, antivirus. I don't know what they're doing in today's world and stuff like that, but I used to have Avera antivirus on my Windows XP machine way back in the day. Everyone remember Avast too. Yeah, that's all I can really remember is Avera and Avast. The good old days of getting antiviruses. McAfee, Norton. Anyways, all right. So this is where I got these numbers. So I mean, I don't know, take it with a grain of salt because I don't know how accurate it is. But the whole point is the probability is not 0, but it's close to 0. So this is supposed to be the probability of a collision with SHA-256. And you can see it right there. It's a very, very low chance. But there's still SHA-512. So, you know, that's another hashing algorithm. And that's 512 bits, which is 64 bytes. And then that's, you know, that output is 128 hexadecimal digits, that hash length. So pretty large length, so the probability should even be even lower with 512. Takes longer to compute though. Anyways, all right, let's move on to a block in the blockchain. So obviously a blockchain has many blocks, and a simple example of a block, and from our demo here and everything, and we're going to be coding this, but I just wanted to put some screenshots of the code in here. But basically a block it has an index, or the block number, whatever you want to call it, and then the timestamp, which is the creation of that block, let's say, the data inside of it, so whatever data is in it, so transactional data or whatever, the current, the hash of that block, and then the previous hash, because it's a blockchain and we want to be able to iterate through each block, and that's how we do it. Is we have the reference to the previous block, and that's how it chains together. So I will go to this demo, and this is pretty neat. This is just another neat demo of blocks. And I'm gonna go ahead, I ain't gonna do the block difficulty yet, but if I go ahead and put in data here, ABC123, I have to go ahead and mine it. And I'll get into what this mining is doing and everything like that. And as you can see, like the hash begins with 4 zeros, and you see I just resetted it. I'll go mine it again, and look at it, found a hash that starts with 4 zeros again. So what is up with these 4 zeros? What is so special about that? So that's what we're gonna go demo right here. But before I do that, you're noticing this nonce number, which is really interesting as well. So basically what that nonce is doing is, and this is what Bitcoin does, and it does surprise a lot of people. But basically, and this is a very simple example. There's more that goes into the block and Bitcoin and everything, but let's just go with, it's basically going to hash the block number, the nonce, the data, the previous hash, and then figure out that. But with Bitcoin, you basically want to find like this perfect, they call it like this perfect hash. There's not really a word for it, but basically it's like a valid or perfect hash when it starts with a specific amount of zeros. And that specific amount of zeros, the more zeros you add at the beginning, it's more computational effort. So as you can see right here, if I do 3, it's going to be really quick, really, really super quick. My computer can handle this, no problem. Here's 4 zeros. Yeah, no problem with my machine. Maybe a machine from 10 years ago. I don't know. Here's 5 zeros. See, it took a little bit more time there. And then here's 6 zeros. Oh no. The thing is that I can't get too crazy because they won't even let me do anything until this is done. I don't even know if I can, yeah, I can't even refresh the page. So I'm doing a denial of service on myself. I can't do anything. But anyways, that nonce, so that's what it's doing. So it is gonna go try it with nonce of 0, and then it's gonna hash it. Does it start with 6 zeros? No. Okay. Nonce 1. Does it start with 6 zeros? No. Nonce 2, hash it. Start with 6 zeros? No. 4, 5, 6, 7, 8, 9, 10. And as you can see, oh, there it goes. Wow, look how many tries it took before it got 6 zeros in the beginning of that hash. That's what it's doing. That's literally all it's doing. So yeah, that's a lot of tries right there. And as you can see, it took 44 seconds, and my machine's able to do about 311,000 hashes per second. Anyways, let's keep going here. Any questions so far about that? And I've been forgetting to put these links in the chat. So let me, hold on. Anyone wants to go play around with that right now? You can. All right. So I just went through a lot of this, but we'll iterate over it again. It might help clarify some things. So a block is considered valid if its hash has a certain form. Bitcoin uses a certain number of zeros in the prefix of the hash for this. The more numbers of zeros in the prefix of the hash, the harder it is to find the knots. Hence, the mining algorithm takes the block information and it keeps incrementing the nonce until it gets that perfect or valid hash. So, for example, and we saw that here's one with, starts with 4. The first block in the blockchain is typically called the Genesis block. You'll hear that. And its previous hash, it's the Genesis block. It's the first block on the blockchain. Obviously, there's no block before that. It's just 0, null, 0, whatever you want to call it. That's just what it is. And then here's the Python code for hash block. So basically, we go ahead and take that index, the data inside the block, the timestamp, the previous hash, and then the knots, encode it with UTF-8, so it's a UTF-8 encoded string. Run it through our SHA-256 hashing function. Boom, we got our hash. All right, so now we talked about SHA-256 hashing. We talked about what a block is. Now we can talk about what a blockchain is. So same exact thing. We have these blocks. These all start with 4 zeros. And it's already mined for us and everything. But here's the thing about the blockchain is if I go ahead and flip this, I break the rest of the chain. And that makes sense because the hash has changed. The previous hash has changed, and that's what breaks the rest of the chain. So I got to remine all of this. So imagine if it was, that was not a lot of computational effort right there, but imagine if I did 6 zeros, 7 zeros, 8 zeros, 9 zeros, 10 zeros. Wow. I mean, that would take a long time to remine and revalidate the entire chain. So that's what the blockchain is. So if I change the first one, I got to remine it all again. And as you can see with the knots and everything. So yeah, that's basically what that is. All right, let me go back to PowerPoint. All right, so how many leading zeros are in the hash for the most recent blocks in the Bitcoin blockchain? So this is actually really interesting. So blockchain.info or blockchain.com, whatever. They changed their name many times. I've been into Bitcoin and cryptocurrency since 2012. So I've seen a lot of things come and go in this whole industry and everything. It's hard to keep track. It changes so much. Anyways, it looks like, all right, so we got block 747994. And look at that hash. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 zeros. Can you imagine how long it'd take my machine to go do that? I don't know if it'd even get done. My MacBook Air would probably just, I don't even know. I don't know. But that's a lot. That would take a long time unless I got really lucky. Unless I got really, really, really lucky. But yeah. So it's interesting because we have the hash, the number of confirmations, the timestamp, the height, the miner who mined this block, and a lot of the blocks that are mined these days is mined by mining pools. You don't really see individual miners, and that makes sense. I mean, would you go into a gold mine by yourself, or would you go in a gold mine with a crew and have excavator? One of your crew members might have an excavator, and another one might have a drill and all that and whatever. I'm basically saying, one of the miners has a really good ASIC rig and you're using just a GPU and stuff like that. So basically you want to work in a pool and get that. And so they mine this block and they got it. And that block reward was 6 Bitcoin. So yeah, that pool is going to go ahead and distribute that Bitcoin that it got and everything amongst the miners, whoever put the most hashing power in and stuff like that. But yeah, pretty neat. It got 19 zeros, so quite a bit of computational effort required for blocks these days in the Bitcoin network. Attacks on blockchain. So I wanted to talk about this because some people are, when they see like you have to remine, when you modify like a block and you have to remine the rest and everything, they're like, well, can't you go do that? How secure is this blockchain and stuff like that? But anyways, the most popular attack on a blockchain is definitely the 51% attack. I think you might have heard of it, but basically you'd have to control more than 51% of the total hashing power of the network. So this would allow you to override the consensus system built and allow for double spending, modify the order of transactions, preventing transactions. I mean, you name it. I mean, you own it. So you want to prevent that 51%. So there are other use cases for blockchain technology, and I always like to, bring this up because, when people think blockchain, they think just Bitcoin, they think Ethereum, Litecoin, I mean, whatever other coins are out there these days. There are many uses and a lot of use cases, and the big thing that comes in, my mind is immutability. Public immutability is like how I like to say it, because it's like, think about it. If you want to have some kind of immutable traceability and have a customer track their purchase from end to end, or recycling, maybe if you want to go recycle something and you want to see where that plastic is going, it's great for supply chain applications is basically what I'm trying to say. Tracing products from beginning to end, know where the stuff that you're buying is coming from and all of that. And it really prevents those supply chain attacks and misleading supply chain metrics. And a great example, and I discovered this, and this is old news, but traceability.starbucks.com, they're using Microsoft Azure blockchain as a service technology, which Microsoft just decommissioned that a year ago. I think it was in 2021. It's no longer called that, but they have like their Azure ledger and stuff like that. They basically, they still have blockchain technology stuff, but yeah, they just renamed it. But anyways, we'll just call it the old name. So Starbucks was using this Azure blockchain technology and basically allowing you to kind of track as a customer. Supposedly, I never even knew this either, there's some kind of barcode or number on the back of a Starbucks bag when you go to like Meijer or Walmart or any grocery store or whatever. And I guess you can scan it and see where the beans came from and everything, and every stop it's made and all that. And it's all, and you're thinking, if they didn't use blockchain, that's the whole point of they're using blockchain, because they think, oh, well, they can just go modify the data or whatever and say that, it's coming from Peru. But no, really, it's just coming from, I don't know, Texas, whatever. I don't know. So I don't know what people think, but it's, so yeah, that's why they use that. They have that public immutable ledger that's showing they can't go change it. That data is immutable. So customers can think that like, hey, yep, it's using the technology of blockchain, and yes, they didn't go tamper with that data, or they're not lying to me. That's exactly where my product has came from. So pretty neat use case. Do you still need miners for those other blockchain uses?
Make sure it's on mute.
Do you still need miners for those other blockchain uses? So the mining is what keeps the network alive. Without miners, you really wouldn't have a blockchain. Now there's other different methods. There's proof of work system, and then there's proof of stake system. as well. And I know like Ethereum is on proof of work. They're looking to transition over to proof of stake. There's been many proof of stake coins. I'm not going to talk about proof of stake. That's a whole another system entirely and stuff like that. But for proof of work coin, yes, you would need miners. Absolutely. Monero, I don't know if anything has changed in the last couple of years. I haven't been keeping up too much up to date with it, but they Monero is CPU only, so you can only mine with your CPU. With Ethereum, it's only GPU, and I'm trying to remember what the hashing algorithm that the script. I don't know if that's what Ethereum uses, but it's called script hashing or script mining, and that was like a GPU only. I don't know if I think they might have script ASIC miners, but anyways, the reason why these Monero did that and Ethereum did want to focus on GPU mining and stuff, because what happened with Bitcoin is people started mining Bitcoin with CPU in the early days, and then they were using GPUs in the early days, but then these ASIC miners came out, and that's basically all it is these FPGA boards that that's its sole purpose is just to hash all day long, and it can just do a ton of hashes per second, way more than your CPU can and your GPU can. So that's where they kind of came up. It's like, oh man, it's just ASIC miners that just own the whole network, and my GPU and CPU doesn't have a chance, or I can't go mine it with my computer. It's a waste of time, waste electricity, everything. But so there's coins that try to battle that. Oh, so there are people mining the Starbucks blockchain. So no, there's no one mining Microsoft Azure's blockchain. I believe what's keeping that alive is it's a service. So Azure is keeping that network alive on the back end for you. You don't really see that. It's just going to work out of the box for you. It does run off like a chain technology like that, and so they're probably they probably have nodes running and probably not just wasting energy and electricity with proof of work, but basically they're just trying to keep that. And that's really interesting, and that's a really good question, how that would work on the back end of Azure with their blockchain as a service technologies. That's a really, really good question. I'm not too familiar with blockchain technology. Any good resources for beginner to gain an understanding? I learned purely from just reading white papers. Everything I have is purely from white papers. So if you go to bitcoin.org, I think it is, they have the Bitcoin white paper. There's Ethereum's white paper. You can go on Google Scholar and read research papers about it, and then basically just catching up with whatever services that are coming out by like the major cloud computing platforms, AWS, Google Cloud Compute, Azure, kind of what services that they're offering. I'm sure there's a ton of YouTube videos now, but back when I was getting into this, there was no YouTube videos. There was nothing on GitHub. There was nothing, so but yeah, so I read a lot of white papers. I'm sure it's a lot easier to get into blockchain technology these days. Or there's talks like this. Funny. All right, so it looks like we're at the coding section. Yep. All right, so let's go ahead and go over to our Python code. It's 7:43. I'm doing really good on time. So, okay. So I already have it coded. I really didn't know what to do here. And I think I remember Dan, like, I think you already had the calculator done and everything. So you didn't like just live code it all right there. But there's not much here at all. And you know what? I really want to, I'll post it in the chat after I'm done sharing and everything. I have this on my GitHub and I'll go ahead and share that so people can clone it down. Maybe that'd be a cool project. I'd be interested if you message me on Discord. I'd like to, maybe get this written in Rust or C++ or C# or whatever, and kind of compare, programming in each one. I don't know, whatever. So, or expanding upon this in Python, maybe putting a GUI in front of it and stuff like that, whatever. I'm cool with whatever. So I'll post that link, but let's get through this. So I just have a constant at the top, and I don't know. The way I define my constants in Python is just all cap variable. So I'd basically just say my hash target is those 4 zeros, and we'll add more and more and more as we run the script. So then I'm a big fan of object-oriented programming. On the current team I'm on and everything, Dow is a Microsoft stack, so I'm basically coding in C#, doing ASP.NET web applications and stuff like that. So I'm just used to that. I really like object-oriented programming. I don't know how else you would neatly program this without doing object-oriented. So basically, we're going to define our block, and we already went through this, but our block has an index, a timestamp, the data inside the block, the previous hash, the nonce, and then the hash of that block. And then within that, we have a method called hash block. And basically all this does is just computes that SHA-256 hash. Now I'm going to go create a chain, create a new class. And basically I'm just going to create an array and a list and define that right at the beginning. And then I'm going to immediately, once that chain is created and that constructor is called, I'm going to go ahead and create that Genesis block automatically. And as you can see, it calls this add block. So then now I have a method called add block, and it just takes in a parameter of data. And basically, if the length of the blockchain is 0, I'm basically going to go create that Genesis block right there. So I'm going to assign that previous hash 0, 64 times. That's all that's pretty much doing. You can do that in Python to make 64 zeros in a string. And then I'm going to go ahead and define the new block. And basically, that's just creating a new block right there, initializing the new object. And I'm going to go ahead and pass the blockchain, or the length, the length of the blockchain. So how many blocks are within that blockchain. So that's the index number. I'm going to get the current time, the data that's passed in via the parameter, and then that previous hash, which is, this is the Genesis block that we're talking about. So it's just that 0, 0, 0, 0. If it's not the Genesis block, I'm going to go ahead and grab the previous block. So we go ahead and grab the last item in the blockchain, which is, this is just a simple blockchain right here. So we just go ahead and that's the easiest way in Python to go grab the last element of the array or list. And then we go ahead and initiate a new object, a block, and we grab the size of the blockchain. We put in the current time, the data that was passed in, and then that previous hash that we just grabbed. And then we can go call our proof of work method with that block and basically get the hash. And then once we have that hash, we can append that block, that new block, onto our blockchain. And I'll just keep going through this and everything. So get chain, easy. It just returns the blockchains just like a getter. You don't really even need it in Python. You don't need getters and setters and stuff like that, like you would in like Java or C# and stuff. And here's our proof of work method. So this is where it's kind of getting into that hashing algorithm and everything. So what we will go do is we'll have a while loop, and basically we are going, and this is basically just grabbing that hash string. As you can see, this is a string. I wish it had like types and stuff. Maybe I should like wrote comments and stuff. But here's that hash string. And what we're doing is we're just grabbing the first 4. The first 4 hexadecimal digits of that string. And if it doesn't equal 0, 0, 0, 0, then we're going to go ahead and increment the nonce, and we're going to hash that block again, which we already talked about. That hash block just takes the block itself and hashes it. And we're just going to keep doing that until that string, that output of the hash function begins with 4 zeros. We're just going to keep doing that over and over. And you saw in that one demo, we were getting up to like thousands, millions before we hit that. And once we have that perfect valid hash that begins with 4 zeros, we're going to go ahead and return that hash. And that's where we saw in that add block method. And then we have the is valid. So basically all this is going to do is, and we saw this in the demo when I changed the middle block member and I had to remind the rest of the block and it's revalidated. You saw them turn all green again. This is basically just making all those blocks green again, all of them valid. It's going to go through all the blocks and validate that all of them start with 000 and stuff like that, and just validate the whole entire chain for us. So very simple. All right, so now we have our main method, and basically we're going to go ahead and create a new instance of the chain. We're going to go add in new block 1, new block 2, new block 3. So in total, we'll have 4 blocks in the end, the Genesis block, the new block 1, 2, and 3. And then we'll go ahead and just go through all the blocks in the blockchain and print them out to see what our hash is and see that whole chain. And then we'll just call the is valid. So, and let me see what version I am on. This will work with any Python version. I've coded this. Geez, I've had this for so long. I think I coded this back in 2017. So I was probably using Python 2 back then. But anyways, 3.9.13, I think 3.9.8 is when they release the native Apple Silicon support. So it should run pretty decent. Python's running natively on my machine. I have a Apple M1 MacBook Air. So we'll go ahead and run that. And like I said, we're doing the 4 zeros, so it should be pretty quick, but it's 4 blocks in total that we're going to have to mine. So let's do it. Quick, not bad at all. So here we go. We have that index number right here. I'll go down that print method. Yep. So we have the index number, that timestamp, that previous hash. As you can see, this is the Genesis block. It's 00000. And then we have our Genesis block is mined, which is 4 zeros. The Genesis block, and there's the nonce right there. So that's how many times it took before it found a hash that began with 4 zeros. Same thing, new block 1, 46,000, 39,000, 31,000, and then the blockchain is valid. So let's go ahead and add one more 0. See what happens. It's taking a while. So, and there it is. So we got our 5 zeros. This one actually has 6 at the beginning. Yeah, wow, how lucky are we to get that one? So quite a bit right there. Wow. What is that, 3 million? Yep, 3.7 million, 320,000, 970, almost a mil. And then is that 4 mil? Yeah, 4 mil. Wow, so quite a bit. I'm going to take out some blocks, and then let's just go down to just the Genesis block. So just do 1 block in total, and let's go up to 6 zeros. Hopefully it's quick. Any questions in the meantime? Does anyone have anything? All right. So yeah, that was pretty quick. That wasn't too bad. Yeah, so we did get the 6 zeros, and let's just, you know what, we got time. Try the 7, see if my machine can do 7 zeros. So as you can think, you know, Python is interpreted programming language and everything. So it's not going to be as fast as if you write in like C# or Java or C++ or Rust or Go, stuff like that. We could definitely increase the speed of this as well. You got to think this is I'm not doing any multi-threading or anything like that. So we could figure out a way how we could have spawn up like a thread pool of 10 threads and then have it go like, okay, you take care of these nonce numbers, this range of nonce numbers, and then this thread takes care of this nonce. I don't know. I'm just thinking like a simple way. I'm sure it could get way more complicated and everything, but yeah, you could definitely multi-thread it and try to make this a little bit more faster and everything. But for the sake of simplicity, yeah, it's going to be. And Dan, you make a good point. Hashlib is in C though. Yeah, so that's nice. Yeah, it would be interesting just to write it. And I think I might have, I don't know if I did in the past or not, but writing in something like C++ or Rust, just that if there's any minor differences and stuff like that in speed. This is definitely taking a while. 7 zeros. Bring up activity monitor. Did it bring it up? Oh, it's over here. Did it get done as soon as yep. It got done as soon as I switched over. Okay, we got our 7 zeros, but let's see what it does. I've never really looked at that. See if we can find Python coming up in here. There it is. Yep, it is native. Let's see Apple there and everything. But yeah, as you can see, it's that process is at 100% CPU, which is not really 100% on Mac OS. I think it will go. I think it goes up to 800%. It's all based on the amount of cores and everything that you have on your Apple machine. But yeah, it's utilizing that thread. It's working it. But yeah, I'll share the link and everything. That's pretty much the presentation. Does any final questions? Anything? Like I said, I promise I'll post the link to the GitHub and everything if you want to grab the code, run it on your own machine and stuff like that. Maybe try like 8 or 9 zeros and have it run through the night, see if it gets done.
Hello. Sorry, I have a question. I just wonder if the values, like the hashed values, are available so we can check them like a dictionary object. So if I have a hash at hand, I want to like do the reverse. So is it possible to like use the hashes from like Bitcoin blockchain? Is that accessible or?
No, I mean, well, you won't be able to reverse the hash. That's the whole point of SHA-256, unless you're literally just basically just going to go ahead and just hash through a ton of like a rainbow table. Like if you're just going to go hash a rainbow table of values and stuff like that and compare it against something, I guess you could do that and guess.
It is like Bitcoin blockchain. Is it something like a rainbow table or something like that? It's not complete, but
yeah,
I mean, at least we have something. So is it possible to use that to check the value?
Oh, check the value of that chain. So yeah, that's a good question. So if I went back to, I don't know what happened to my browser. Hold on. Let me go back to that link. There it is. Yeah, so the thing is with Bitcoin, I think it takes I don't know how much of the data it takes to hash that. That's a really great question, and I wanted to look into that a little bit more. But basically, you know, we got the hash, the timestamp it's going to hash. I don't know if it takes height into consideration. That's the whole thing, is like what makes up a block in the blockchain. But I don't know if I don't really think you're going to be able to just simply hash that and validate that. You'll have to get all that information together unless there's something someone built online and stuff. But as you can see, there's somewhere where it tells you the amount of transactions that happened within that block. Yeah, right here. There was a total amount of 18,000 Bitcoin that were sent in this block with an average transaction of 11 Bitcoin. And I don't know if there's, yeah, right here, the transaction volume. There's a lot of transactions within this block. So yeah, you'd have to get all that information and hash it and with that nonce number. This doesn't even tell you the nonce number, this website. I've never seen that like on something either. But yeah, good question. Maybe someone's built something. I was looking into that. Maybe we can figure something out on the Discord.
Yeah, thank you very much.
Yeah. Any other questions? All right, cool. All right, let me grab that link, and there's no other questions. Dan, I mean, take it away. I'll stop sharing and we can close up.
Yeah, thanks so much, Brad, for coming and presenting. That was a really great introduction to hashing and blockchain and Python. So we really appreciate it.